All right, welcome to Lecture 1, Part 2, the Real-Time DSP Lab course at the University of Texas at Austin. Any questions from last lecture or previous lectures? So this is Part 2. So in during last lecture, we were coming off a long holiday weekend. So last time we talked about bandwidth, definition, and some ways to measure that, and the role of sinusoids in upconversion using sinusoidal amplitude modulation. And then this is just a snapshot, a LabVIEW snapshot of sinusoids in action. So I'm going to skip on to third and fourth topics here in Part 2. So this is a preview for Lab 2, which starts next week, starts on Monday. And in Lab 2, you'll generate sinusoids on the digital signal processor. You'll program them in C, and there are a couple ways to do that. In fact, you look at 3 ways to do that. So the first thing to do is compute the amplitude values of the sinusoid, both cosine and sine. And there are 3 ways to do that. We'll talk about each one today. You can call a C function, can pre-compute one period of the sinusoid and store the values in a lookup table. And third is use a difference equation. And on homework 0, I've asked you to look at the difference equation in one of the problems. Okay, so we'll look at that today, the 3 different ways to compute a sinusoidal waveform. There are more than 3. These are 3 very common ones. And they each have trade-offs. So this is the first lecture where we'll get into some really good discussion of signal quality versus implementation complexity trade-offs. There are seats. Oh, okay. There's one seat in the back if you'd like. Right. Then once we've computed the value for the amplitude, either one amplitude at a time or a block or a period of amplitude values, we want to get that off the chip. And there are a couple ways, 3 ways we can do, well, 2 ways we're going to do it in lab, and we'll do a 3rd way in lab 3. So 2 ways we're going to do it is we're going to pull a data transmit register, and when it's ready, we give it the value we need. We can also generate interrupts, software interrupts from the converter, in this case from the digital to analog converter, to service the data now that it's ready, or to actually get the data onto the peripheral because the peripheral's ready. And then in both cases, the 3rd case, which isn't up here, which is to take a block of data and get it off the chip at one time. This is known as direct memory access transfer, which is very common used in instrumentation and processors. And that's going to take a block of data and get it off chip all at one time instead of one sample at a time. And then no matter how we get the data off the processor, we're going to do the calculations, and the computation will be done in floating point. So we'll do everything in 32-bit float. Now we'd like to then take that data and get it off the chip, which means we're going to use a digital to analog converter, and that digital analog converter on your board has 2 channels. And each channel is 16 bits. So I have 2 channels, 16 bits each. So that means that I can read or write a 32-bit value. And that 32-bit value will have, it's actually 2 channels, so each channel is 16 bits. And if I can concatenate that, I get 32-bit value. So if I want to transmit or send data from the CPU core, the processor off the chip into the D-to-A converter, I'm going to write a 32-bit value. If I use the same codec chip, this is an AIC codec from TI, then I would read a 32-bit number. I get 2 16-bit values, one from each channel of the converter. So it's the same chip, it has 2 functions. So when we set it up to do D-to-A conversion, we have to worry about how to convert 32-bit float to a 16-bit integer. And if we don't do it right, we don't get a very good-looking sinusoid. We'll talk about that on the next slide. So expected outcomes for the lab, this is our first good exercise in signal quality versus implementation quality or implementation complexity trade-off. And we're also going to explore interrupt mechanisms. Now, from the book, from the lab manual by Welch, Wright, and Morrow, the interrupts and all that, all the interrupt handling is defined for you. So it's a matter of plugging in your C code as to define the interrupt handling function. But all the details of configuration are done for you in the C code from the lab manual. Yes? So
when you say pulling data transmit register and software interrupts, are you talking about two different methods?
Correct, two different methods to get data off. Because we're trying to get, again, data from the processor to another chip external to the processor, which is...
The quantization happens separately.
Quantization is going to have to happen in the processor. So you're going to send the quantized data to the D to A converter. So you compute in floating point on the CPU core, and then you'll have a peripheral controller on the processor itself that the CPU will then send data to. But the CPU has to get the right data format, which in this case is a 16-bit integer. So we're going to have to scale the floating point data correctly so it goes through the D to A converter correctly, and you see it correctly on the oscilloscope in the end. We'll talk about that on the next slide. Go ahead.
So I was just going to say, so in other words, are we typecasting it in software?
Yeah, if you do a typecast, we're going to see quickly that will give you an interesting sinusoid, but not the one you want. If you just do a straight cast and see. Right, that's a way to do it, but it's not. We need to do a little more work than that. We will cast it in the end, but we have to do a little work before we cast it. All right, so let's connect continuous time and discrete time. And in the same approach, we're going to connect continuous time frequency and discrete time frequency. So so we think about what we're going to try to generate. We're going to try to generate a one-sided discrete time cosine or sine signal with a fixed frequency, omega naught. And omega naught will be in a discrete time frequency in radians per sample. So the function or signal that we want to generate has a pretty simple mathematical form, which is this. It's just a one-side cosine. The one-sidedness is enforced by the step function, right? So from the step function is defined in discrete time. It's nicely defined in discrete time. So U of n is going to be 1 when n is greater than or equal to 0, and 0 otherwise. Right, so it's a very simple, turns on at 0 and stays on. And by on we mean 1, and by off we mean 0. Okay. Now there are lots of ways we can do this, and they each have different complexities to make this equation happen. And so let's go back to continuous time to see how we get to discrete time to make sure we can make the connections, because ultimately you're going to generate a cosine of a fixed frequency in hertz. You have to worry about mapping that back to discrete time. So consider a one-sided continuous time analog amplitude cosine of fixed frequency f naught, and f naught now is in hertz. And we'll figure out how to connect the f naught in hertz to omega naught in radians per sample. So the one-sided cosine in continuous time has the same form, right? It's just that we now have to worry about continuous time little t, and make sure that the units inside the argument of the cosine is still radians. And let's check that. So I have 2 pi, which is radians. So this gives me radians. F naught is cycles per second, and t is seconds. So the seconds cancel, and I end up with 2 pi. 2 pi radians. So that's good. The units check out. And then the one-sidedness is enforced by the step function. Now, in continuous time, the step function has a slightly different form. But for the purposes of this derivation, we're going to assume that it has the same form here. There is some ambiguity in the step function at the origin. We'll talk about that in Lecture 3 in Signals and Systems Review. But for now, we'll just say that it has the same form. So it's 1 when t is greater than or equal to 0, and 0 when t is less than 0. Again, that's not the only definition, but again, because you have flexibility at the origin, how you define the amplitude. But for this purpose, it's going to be 1 at the origin. So now let's go ahead and sample the continuous time one-sided analog cosine. And we do the sampling by substituting in little t is some integer multiple of a sampling time, t, capital T sub s. Now the sampling time is 1 over the sampling rate. So I can either substitute in t, and what I'm going to say by sampling is I take uniformly spaced samples in continuous time to get my discrete time signal. So I can either substitute for little t, little n times capital T sub s, the sampling time, or I can substitute n divided by the sampling rate. It's the same answer, the same value. So let's do that. So if we substitute in little t into this continuous time analog cosine, then we get, for every time we see little t, we're going to replace it with, and I'm going to go with n over fs for this particular derivation. All right, so little n, the little t becomes little n over fs. So the argument in the step function is n divided by fs, and then the argument of little t here, or the value of little t in the argument of the cosine, little t becomes n over fs, and so f naught over fs, I can collect that, and finally I get 2 pi and then times little n. Now, I'll show the derivation for this. What's interesting is to get from continuous time step function to discrete time step function, I have to figure out how to deal with the conversion, because what I'm going to do here is take, when I sample little u of t, at t equals nts, I now have u, and the argument now is n times ts. Now the problem is I like to be able to reduce that to the discrete time step, but I have the scaling factor of t sub s. So we'll talk about derivation for how to get there, but we're going to get there, the way, ultimately the bottom line in this is that we can write this as a discrete, basically as a step function. We can pull out this scaling factor, and I'll make an argument for this based on the area in a function that you'd scale in time. We pull out the 1 over ts, now scales u of the step function. And now I'm left with just u of little n, which I can put that down as discrete time. So that's where this gain term comes from, this 1 over t sub s out front. So that feeds into that. Okay. Now this is the mathematical equivalence, and in practice we're going to have to adjust the gain anyway, but this is just the mathematical equivalence, and then we'll talk about implementation. So the derivation to show how to take the step function in continuous time, sample it, and show that it's 1 over the sampling time times the discrete time step. To wait a second for the transition to the document camera. All right. So this is a more general result than just for the step function. So if I have a function that I'm scaling in time, and time is where I'm integrating against, then I can rewrite this in the form I showed you earlier. And the way you go about that, a way to go about that, is to look at the possible options. So if this doesn't work if a is 0. Right? So we're going to exclude a equals 0 here. So when a is greater than 0, we can just use substitution of variables, let u be our new variable, and it's simply what is in the argument little a times t. And if we isolate t, it's just t equals 1 over a times this new variable u, and dt is 1 over a times du. And limits of integration stay the same, minus infinity to infinity. Okay, so that gives us the outcome for when a is positive. We can rewrite the integral over all time. This is down here as simply the 1 over a times the integral of x. So in terms of keeping what happens to the area when you do a variable, when you have a scaling in the time domain by little a, the effect on the area is the area of x gets scaled by 1 over a when a is positive. This is a general result. Secondly, we can do the case when a is less than 0. When a is less than 0, we can do the same kind of variable substitution. The limits go to different values. So when t goes to infinity, this is when u goes to minus infinity because a is negative. And when t goes to minus infinity, u goes to infinity. So limits of integration get replaced by infinity to minus infinity of x of u 1 over a du. We can switch the order of the limits by negating. So now I have minus 1 over a times the integral from minus infinity to infinity of x. And then I can simply combine these two results, noting that minus a is really the absolute value of a here because a is negative. Okay, so I'm left now with a more general result, which is going to be useful in many, many cases through the semester. We'll need this for the Dirac delta functional later. This is pretty useful stuff. So this is the kind of the bottom line where it's useful. So if I scale the time axis by little a, and a is not 0, then the change in the area is 1 over absolute value of a. Right?
Why again do we go from infinity to negative infinity? Sorry.
So if you when a is less than 0, and you look at what happens to limits, so the original integration is from minus infinity to infinity. Right? So when I substitute in t equals 1 over a times u, I then have to look at what happens to the limit. So as t goes to infinity, u goes to minus infinity because a is negative. That's one. I get a sign change. And so here I'm integrating from infinity to minus infinity to switch that and make it what we would prefer to have, which is minus infinity to infinity. Then we simply can negate. Right. And then finally, so how does this relate to our particular issue at hand, which is take the step function, sample it. And now I have these uniformly spaced samples of the step function. What is the equivalent effect in the area? It's scaling the step function by 1 over capital T sub s. So this is equivalent to 1 over the sampling time, or equivalently the sampling rate. Okay, this is an argument to preserve area. One way to argue this. Okay, so these two lines are the critical results. Right? And again, we'll need this more general result later. All right, now that's the theory. Theory's wonderful. Starting point. Now let's talk about how we actually do it in practice. So the theory the theory is also very useful in that it now relates continuous time frequency to discrete time frequency. And this we'll use all the way through the last lecture for the semester. And it even shows up on interview questions, apparently. Talking to a student before taping. So this is the relationship. And it's not something to memorize, although if you use it enough, it may become internalized. That's fine. When I need it, I go back to the starting point, which is the continuous time one-sided cosine. And it's okay if you make it two-sided. We can even get rid of the step for the purpose of theory. And sample it. And just from one line of maybe 2 lines of work of algebra, you'll see the connection. That the discrete time frequency is all this in front of little n, right? It's the omega naught. So it's 2 pi times the continuous time frequency in hertz, f naught, divided by the sampling rate, f sub s. This is a profoundly simple relationship and also profoundly useful, because if you know two of the terms, you can get the third. So the use in Lab 2 is you have a certain sampling rate, which is 48 kilohertz in lab, 48,000 hertz, and you're asked to generate a cosine or sine, in this case cosine, with frequency f naught. So no matter how you implement the generation of the sinusoidal signal, I need to know what omega naught is. And the way you can get omega naught is simply 2 pi times f naught divided by fs. So as an example, if we look at, this is a different sampling rate, but the idea is the same. So if I take a continuous time frequency of 1200 hertz, a sampling rate of 8000 hertz, the discrete time frequency, just running the numbers, is 3 over 10 times pi. 3/10 pi. That's it. And that's the value we need no matter which of the 3 ways to implement the cosine that we choose to use. Right? Function call, lookup table, difference equation. We need to know what omega naught is. Now, in practice, the next thing we have to worry about is the gain. Okay, so the gain that's here from the theory says we should scale the cosine by 1 over the sampling time, or equivalently, 1 over the sampling rate. Okay? That's the theory, and that's to preserve the area of the one-sided cosine in continuous time in the discrete time case. We don't have to do that. We don't have to preserve the area. So it turns out this will, it's okay if it bothers you right now, but the gain is something that we are going to allow to vary, and we're going to just change it when we want to. I know it sounds a little bit weird. So in any system, in any signal processing system, the gain is something either the user controls, like turn up the volume when you're playing audio, or the receiver in the system is going to automatically adjust anyway through a process called automatic gain control, which we'll talk about after spring break. So in either case, the gain is something that we have to get right eventually, but we can change it whenever we want to, as long as some other part of the system will figure it out and get it right. The gain is kind of flexible. Other than a gain of 0 doesn't help us, but we're flexible and keep on a gain that's not 0. In this particular case, for Lab 2, we're going to compute this cosine as a 32-bit float. We want to convert it to a 16-bit int. The cosine has values between 1 and 1 in amplitude. With a gain of 1, what's the cosine is between -1 and 1 inclusive, right? If you directly typecast that floating point value to a 16-bit signed integer, what possible outcomes do you get? You get -1, 0, and 1. Only 3 possible values. It's not, so it is a periodic waveform. It's a staircase approximation. It's a rectangular pulse, if you will, or pulse train, which is great if you want to generate a rectangular pulse train. This is exactly a good way to do it, great way to do it. If you want to generate a cosine, then you want to use the scaling to your advantage. So what kind of scaling value could you use before you did the typecasting? Multiplied by 100?
Or by your resolution.
By your resolution. So if I have a 16-bit signed integer, what's the resolution here? What's the maximum integer value? Which is 32 minus 1. Okay. That is important.
You should remember that.
The minus 1 is important. So what is that? 32,767. Okay, so that's the maximum positive value. So you could map the 1 in the floating point domain to 32,767 as a 16-bit int. And you would do that by setting the gain to be 32,767. That's pretty extreme. You don't have to go extreme. Maybe 30,000 is enough. Maybe, 25,000 is enough. But leaving the gain 1 isn't going to look all that great as a cosine waveform on your oscilloscope. All right, so we're going to let the gain be flexible, and we're going to change it as we need to change it.
So is that actually way how they generate it, like a full string without having to code more data into memory?
Yeah, so if you really want to generate a pulse train, you really just have to generate 1 minus 1. You don't really have to go through. I mean, you don't. This is a lot of computation to get a cosine and then just, typecast. There are faster ways to do this, which is just you let it be 1 for a certain number of samples and then minus 1 for a certain number of samples and repeat that. It's a very fast algorithm to do that. This would be a very slow way to generate that.
Yeah. I was just...
Right. So it's not. Yeah, we would do it a different way than this. Okay, any questions on? So a couple of big things here. Discrete time frequency omega naught. You'll need this for the whole semester, and probably if you do any work with sampling anything, which I think is everything we do, regardless of your field in electrical computer engineering, at some point you have to sample and take measurements, whatever. This is an extremely important relationship, but one I'd recommend that you derive when you need it, as opposed to memorize. And second is gain is flexible, and we're going to use whatever gain we generally want to use. Okay. There are a few times we have to be very precise on the gain. It happens in down conversion, for example, if you just look at modulation and isolation. But in practice, like I said, either the user turns up the volume or the receiver automatically adjusts the gain. So usually you're off the hook on getting it just right. Usually. All right, so let's go through some ways to generate the amplitude values. All right, so the first one, kind of the first thing I would think of is to use the CMath library. The CMath library's got a cosine COS function in it. It's got an SIN for the sine function. Straightforward math library call. Now, there's some downsides. The math library call in C uses double precision floating point arithmetic. All right, so on your processor in lab, which is a 32-bit processor, single precision float, the data type float in C is 32 bits. The floating point format for double is what? 64 bits. Okay, so 64 bits of floating point is simply more than we need. We just don't need that much precision. So 64-bit IEEE floating point means 53 bits of mantissa plus sine, 11 bits of exponent. That's just way more resolution than we really need. I have never used in any embedded system I've ever built, and built a few, remember from lecture 0, never used in the embedded system a 64-bit float. Now, I've used it on the desktop in MATLAB simulation because that's by default going to be in double precision. Fine. But on the embedded system implementation, I've not needed that much precision. Who knows? Maybe tomorrow I'll come back and say, well, we finally used it. But in doing this for 17 years, we just not used it. We just didn't need that much precision. Good for desktop simulation, but not, a little bit over the more than we need in an embedded implementation. And there are some embedded implementations that use 64-bit float. I'm not saying they're not, but from my experience, I've not seen it. So there's now another downside. There's no standard in the C language for the internal implementation of the math library call. We don't know how computationally complex it is. We just don't know. It's dependent on the library that you call. So this approach is really useful. It's appropriate for desktop computing. We want high accuracy, circuit simulation, whatever happens to be, communication simulations. More accuracy is a good thing. Why not use it? But in embedded scenarios, implementation resources are generally at a premium. We're kind of squeezing every last cycle out of the processor to get the cost down. And so usually alternate methods are typically employed. So let's go on with the complexity, though, of using the math library. Because who knows? You may end up using this in an embedded system. It could happen. So to find an example of an implementation, I went to the GNU Scientific Library and looked at the cosine function. in the cosine function, I used this is now an older version. I looked at the code and I noticed a few trends. One is there's an 11th order polynomial to compute 1/8 of the period of the cosine, and it gets the other values from symmetry. So that's kind of cool. It uses symmetry in the waveform to compute a smaller. So you can say, well, 1/4 of a period makes some sense, 1/2 of a period makes some sense. It turns out 1/8 of a period also you can replicate the entire period just from 1/8 of the period. If I looked at all the calculations involved in the C code implementation in the GNU scientific library, I ended up with the following. For every value of the cosine function, for every amplitude I needed, I had to use 20 multiplications, 30 additions, 2 divisions, and 2 power calculations per output value, all in double precision floating point. That's a lot of calculations for one value. And they also had some extra code to estimate the error, which is useful for high accuracy desktop simulation. That part of the code we wouldn't need if this were to be in the embedded space. Okay, so just to give you, and this is a trick they use. So this is a really nice trick. I think I'm sure it goes back at least to the 1960s, if not earlier. This is a very efficient way to implement a polynomial calculation. Might use it sometime in the future. So the direct form of the polynomial, 11th order polynomial, right? I have x to the 11th power times the coefficient x to a11 or a11 plus a sub 10 times x to the 10th and so forth. And if you look at the direct form calculations, I'm doing a lot of the same calculations over and over again. If I separately compute x to the 9th from x to the 10th, I'm just recalculating y. So if I'm going to do x to the 10th, I can just take x to the 9th and multiply by x. It's much faster. Go ahead.
Is there a reason why they don't use like 12th or 13th order?
Right. So what this was is a curve fit. So they looked at the 1/8 of the period of the cosine, and they tried to fit it with a polynomial that got to a certain amount of error. So in that, and I didn't revisit that, how they got there, but this apparently gave them enough accuracy over 1/8 of the period. And so if you did, sure, a 12th order polynomial in principle should be more accurate, but it takes more calculations. Now, one of the weird things about polynomial fits is if the order is too high, you get these bizarre deviations from the curve that are like really weird peaks and valleys. So if your order is too high, you don't get a better result. At some point, you can get actually the quality actually degrades, which is interesting. So the GNU folks who wrote this version in the GNU scientific library picked 11th order. I don't know why they picked 11th, but it works for them. Now there's a Horner's form which basically factors out each successive use of x, starting with x and then x squared and x cubed, and it gets this kind of nested form which reduces the number of multiplies dramatically. It's kind of a cute trick. So if you look at direct form, so if you look at what happens, I nest these first two, I pull out the x in common between x11 and x10. And so I get a11 times x plus a10. I take that quantity, multiply by x, add to it a9, take that quantity, multiply by x, etc. And this nested form reduces dramatically the number of multiplication operations by a factor of 6. It's dramatic. And there's no change in the, at least there's no change in the calculations. I'm just reordering how I'm doing them. There is another advantage, which is the intermediate calculations do not have a wide of dynamic range or possible amplitude values doing it in Horner's form versus this one. So there is a benefit with numerical accuracy in the Horner's form, as well as a benefit in the implementation complexity. Okay, so it's a win-win to go Horner's form. Savings in calculations, better numerical accuracy. So in terms of a signal quality versus implementation complexity argument, this would be a way to go. Horner's form is a win-win. You improve quality, you reduce implementation complexity at the same time. Doesn't happen very often to do both at the same time. All right, so that's Horner's form. And that's the the CMath library call. That was method 1. So method 2 is a difference equation. And in the difference equation, we're going to dramatically reduce complexity, but we're going to pay a price as the signal quality won't be as high. Do a trade-off. And this is right from homework 0. So here is y of n, the current output value. We're now going to reuse previous calculations to compute the current amplitude value. And in homework, you'll show that this difference equation will give you a cosine. So I have a difference equation that involves the previous output value, the output value 2 samples ago, the current input value, and then the previous input value. Okay, so x of n minus 1 is the previous input value. So not a lot of complexity here. How many multiplies do I need for one output value? 2. How many additions? 2 argument additions. How many 2 argument additions do I need? 3. Pretty low complexity. And I can do this in double precision float, single precision float, and integer arithmetic. So I can do this in 16-bit integer. There's some scaling I have to be careful about, but I can do this in 16-bit integer, 32-bit integer. I can do it in floating point. A lot of flexibility in the data type and arithmetic I use with the difference equation. It's under your control as the implementer. Now, where this difference equation comes from is it comes from the inverse Z transform of the Z transform of a one-sided cosine. And that's what you'll explore in homework. The impulse response of, so it's basically an impulse response of a system. So what does that mean? It means that I have a system, and if I put in a discrete time impulse, I get out cosine omega naught n times the step. And this is an LTI system, has an impulse response h of n. So the impulse response is exactly the one-sided cosine. And just for definition, the discrete time impulse is defined how? What happens at the origin? It's 1. And elsewhere? 0. Right, so it's 1 when n equals 0 and 0 otherwise. It's an impulsive event. And when it occurs at n equals 0, so it's on at n equals 0 and off otherwise. So that also is interesting because it tells us that in this case, x of n, the input, is nothing but the discrete time impulse. So most of the time it's 0 actually. It's only 1 when n is 0. Right.
Do you just assume that the input is a delta function?
But this is the notion of an impulse response. So the definition of an impulse response is it's the response of the system to an impulse. That's it. So we're right. So what I'm saying here is this difference equation, which relates the input x to the output y, has an impulse response that's exactly the one-sided cosine. So the way to think of the system is if I have x as an input and I have y as an output, then another way from system theory, what's another way I can compute y? If I know the input x and the impulse response h, what's the relationship? It's the convolution. It's the convolution in the discrete time domain. It's the product in the Fourier domain. I heard product. It is the product in the Fourier domain. In the discrete time domain, it is the convolution. And we will review convolution when we do lecture 3. Slides on signals and systems. That's next week. If the input is the impulse, then the output is the impulse response. More generally, if the input is X, the output is Y. I can do that through either convolution, or I might be given the relationship as a difference equation. The sine has a similar difference equation. What changes is x of n isn't there, and cosine omega naught becomes sine omega naught. And I think I think what happens. I have to look up what happens to the minus sign. But anyway, the sine term to generate the sine function, it's the same difference equation. These two terms are the same. This goes away. This becomes sine of omega naught. Now, for a system to be linear and time invariant, we'll show this a little bit later. One of the necessary conditions for linearity and time invariance is that the initial conditions have to be 0. So it means that when I start this difference equation, when n equals 0, the value of y of minus 1 is what? 0. The value of y of minus 2 is 0. The value of x of minus 1 is 0. So this implies that when y of minus 1 is 0, y of minus 2 is 0, x of minus 1 is 0. Computations again, 2 multiplies, 3 adds. Memory usage, 2 coefficients, 2 previous values of the output, y of n, 1 previous value of the input, x of n. Pretty low complexity. There's some drawbacks. The error increases as n increases due to feedback. Every time I multiply 2 numbers together, I get more bits than I started with. So if this were, let's say, 32-bit float and 32-bit float, the worst case result, so 32-bit float has 24 bits of mantissa plus sine, 8 bits of exponent. So if I multiply these together, I need 48 bits of mantissa. I get more bits, double the number of bits of mantissa. But in implementation, I'll truncate this back to 32-bit float. So I take the 48 bits of mantissa, truncate it back to 24. So that rounding error will propagate to future calculations because that rounding error will already affect the current output value. And then that's used in the next calculation. So it keeps cycling or building on itself. So there's ways we can overcome that one. The next one is that this one works for a fixed value frequency, which for many cases this is fine, but there's sometimes we'd like to adapt the frequency value. All right, so let's see some ways we can address both of these. Okay, so if we implemented the difference equation with exact precision coefficients, infinite number of bits basically, and arithmetic, we'd have perfect quality on the output. But as I said, we get some loss as we go. There's already some loss in the coefficients, except for very special values of omega naught, right? Because the cosine gives us a irrational value, except in a few special cases. And we're going to lose precision when implementing the irrational or approximating the irrational value with a 32-bit float. There's already error right there in the coefficient value. And then we get the additional error of this truncation and rounding of all the multiplication results. And also for addition, if I were to add 2 8-bit integers that are unsigned, how many bits, worst case, do I need? If I add 2 8-bit numbers, 9, because I can get a carry. So even with addition, for every addition that I do, I lose a bit of accuracy. For every multiplication I do, the accuracy is much worse. It's the number of bits of accuracy of one of the multiplicands. It's how much I lose. A lot. So a couple things we can do in practice. We can do the following. We can kind of, I say reboot here, kind of tongue-in-cheek, but reboot the filter after every period. So we're going to try to generate a cosine. So once we get to the end of the period in discrete time, we reset the filter, which means that we set the initial conditions back to 0. and restore the input to be the discrete time impulse. And this will reduce the loss because it means that all the error only really propagates through one period of calculation, not to the next one. And at the end of one period, it also allows us to change the value of the frequency omega naught.
Wait, so you set the ICs back to 0?
Yep. So you set y minus 1 back to 0, y minus 2 to 0, x of minus 1 to 0, and you change the input to be the discrete time impulse. So you basically go back to what you did at the beginning of the previous period, which you can do because the signal is periodic, and it's okay. You just want to really regenerate the same period again. All right, here's the third option, which is lookup table. In a lookup table, we're going to pre-compute the samples we need and store them in a table. So the computation can occur offline on your desktop, get really high accuracy answers. Use the CMath library if you want. It's offline. It's on your laptop, PC, whatever. And then take the values computed in this high accuracy way and store them in a table, in an array, on your embedded processor. And then just read the values as you need them. You don't have to do any multiplies to do that. So then now some questions that come up. Okay, how long is the table going to need to be? Well, it's going to be one period of the discrete time cosine, half a period, fourth of a period. But I have to know what the period is. So to find out what the period is, it's kind of interesting in discrete time. Here's remember our formula for converting continuous time frequency f naught and a sampling rate fs to discrete time frequency is this 2 pi f naught over fs. So what I can do is I can remove the common factors between f naught and fs until I get an integer relationship, capital N over capital L. And if you remember in the previous example, we had f naught is 1200, fs is 8000, f naught over 8000, a lot of common factors we can remove. We get down to
3 out of 20.
3 out of 20, that's right. So f naught over fs, we can finally reduce this to 3 over 20. And so our capital N would be 3, capital L would be 20. So we can reduce this to a ratio of 2 relatively prime integers times 2 pi. Now, some interesting ways to read off this, because a period in discrete time doesn't necessarily match a period in continuous time. And the reason for that is in discrete time, we're on an integer grid and not a real valued grid for the time domain. So the discrete time period is actually L samples. And those L samples contain n continuous time periods. So when n is at 1, then the discrete time period and continuous time periods are equal. But when n is not 1, they're not equal. All right, there's a derivation for this. I'm trying to... may have to add that later. All right, there's a derivation for this, and basically it comes down to you'd like to know that at what value of little n does this repeat? Okay. The periodic waveform says that if a system is periodic, if I add to it, we'll call it n naught as an integer, and if n naught is the period, then it's the same as xn. Okay. So derivation, if you do this, will show that the only way that you can get a periodicity here is when little n is L, basically to get rid of the denominator, and that's going to be your period. So let me see if I can wrap up. There's also another comment here. There's a built-in lookup table on some processors. The one in lab, we don't have this. There are some processors that have built-in read-only memory in the CPU tables of cosine theta and sine theta sampled 1 degree apart. And if they're there, just use them. Okay. So to kind of summarize the design signal quality versus design trade-offs, again, we want to generate a cosine, one-sided. The discrete time frequency has the following form: 2 pi times capital N over capital L, where capital N and capital L are integers, positive integers. And here are the 3 methods. C math library called difference equation lookup table. Max here refers to multiply accumulate operations, so much more here. C math library call is the highest in complexity in multiply accumulates. It also takes up a lot of memory. The lookup table could take up more memory, depends on the value of L. In the C math library call, everything is in floating point. It doesn't have a fixed point version. The difference equation, you can do it in integer or float. In the lookup table, you can do an integer or float. Totally up to you. And so for trade-off, the C math library gives you the best quality, most complexity. Difference equation is low complexity, but also low quality. And finally, the lookup table is kind of a lot of memory, no math, no multiplication. It gives you incredible quality. So using an embedded system, it's one of these two. It's either difference equation or lookup table for these trade-off reasons. All right, thank you, and I'll see you on Friday. Homework is due on Friday.